The purpose for this lab is to observe the motion of an object falling from rest and to compare it to two computational models that will be based on the principles of Newton's second law. One will model an object falling affected only by gravity, and the other will model an object falling affected by gravity and a drag force. We are interested in seeing this because it will allow us to better understand why objects fall at the speed that they do and what forces are acting on it. We will first begin by looking at our observation in Tracker. Then we will program our two models using GlowScript. Next, we will compare the three data measurements and discuss their similarities and differences. Then we will answer some final discussion questions and conclude. Let's first look at our observation. Here, I chose this blue ball as my system. The origin is set at the center of the mass of the ball, and the length of the ball is calibrated for 0.08 meters. The ball will be moving down in the negative y direction. With these settings, we are able to collect our data regarding our position and velocity. Now we will create our two models. Our first model will be an object falling with only the effect of gravity. Our system will be the blue ball and the surroundings will be the ground. We will be using an iterative process to predict the motion of the ball based on the momentum principle. The following equations will be used to calculate our net force, predict our new velocity, and predict our new position. To calculate our net force, we need to find our weight force by multiplying our mass by negative 9.8. To predict our new velocity, we will add our current velocity to the net force divided by the mass and multiply it by our time interval. To calculate our new position, we will multiply this new velocity by our time interval and add it to our current position. We will repeat this process every 0.001 seconds until we reach 0.783 seconds. We are choosing this model to examine our system to see what the motion of our object would look like if there were no other forces acting on the ball. If we run this program, we can see the ball falls down with increasing velocity. Now we will model an object falling with the effect of gravity and drag force. Our drag force is going to be pushing opposite to our gravitational force. Our system will remain the same, the blue ball, with the surroundings as the ground and the air. We will use the same iterative process to predict the motion based on the momentum principle. The change we will make will be calculating our drag force. Mag_vol is our speed, which we squared and multiplied by b in our unit vector to get our drag force. This model was chosen so that we can get a more accurate model of the motion of our ball, one that is affected by both gravity and air resistance. Note that our drag force is positive and our weight force was negative. Now we will add the two together and run. Now let's take our data and compare it to our observation. I graphed all three on the same graph with all the same initial conditions. Our initial position is 0, 0, 0 meters. Our initial velocity is 0, 0, 0 meters per second. Our starting time is 0 seconds, and our ball's mass is 0.0045 kilograms. We can see that our observation more closely matches with our model with drag. The slight discrepancies you may see could have been caused by slight incorrect calibrations in Tracker, such as not having the exact length of our blue ball. This length not being exactly correct can greatly affect our data. We could have also had varying centers of masses at each frame. Using this data with potential varying positions could give us a slightly off velocity. Because the momentum principle relies heavily on our initial velocity, this could cause some error. To improve data agreement in the future, the best I could do is make sure everything is calibrated perfectly. Our gravity without drag model is very off from our observation and gravity with drag model. Along the graph, this model has a lower y position than the other model and our observation. This is as expected because if an object does not have an opposing force to the gravity, then it will fall further as time goes on. This is different than our observation though, because our blue ball did in fact have opposing forces, air resistance, which is why it closely follows our gravity with drag model. Here, we have a velocity versus time graph of our two models. We are asked if any of the models predict a terminal velocity. A terminal velocity is the speed that a free-falling object will eventually reach when it is no longer accelerating due to resistance of the medium it is passing through. We can see that neither of the models reached a terminal velocity in the time frame of 0.783 seconds, but we can see that the model of gravity with drag force is slowly reaching the point of what we can only guess to be constant velocity. On this graph, I increased the time interval to 1.5 seconds. We can see that the model of gravity with drag did indeed reach a terminal velocity of about -5 meters per second. We can assume our model with no drag will never reach a terminal velocity, especially since there is no visible curvature. What if the ball was thrown down instead of dropped from rest? How will this affect our terminal velocity? Here, I gave the ball an initial velocity of -3 meters per second and I graphed it. We can see that there is still no terminal velocity for our model with no drag, but our model with drag, we have the same terminal velocity we had before. The difference is how quickly it reaches its terminal velocity. We can deduce that it reaches the terminal velocity quicker because it did not have to gain velocity starting from 0, because it had an initial velocity already. To conclude, we started out this lab by observing the motion of a ball moving at constant motion. Then we predicted with Newton's second law the motion using two models, one that took only gravity into account and the other gravity and drag. Then we compared the models and finally we discussed the presence of terminal velocity within our models. Thank you.